Welcome back to my course Industrial Biotechnology. Now in the last lecture I tried to discuss about the immobilization, about the enzymatic reaction kinetics and how enzyme can be used for the producing different products, and also we tried to do the reactor analysis, how we can get that desired amount of product by using batch process, by using CSTR, continuous start tank reactor, and the plug flow reactor. Now today I want to discuss one important techniques that we have for the immobilization of the enzymes, which is largely used by the industry, because when we use the enzyme, as you know that enzymes are mostly they are protein in nature, and protein with active sites we consider them as an enzyme, and after when you carry out any kind of enzymatic reaction, after the reaction is over, that enzyme remain as impurities in the reaction mixture. So that is to be discarded, that is to be purified. So and another disadvantage is that you cannot reuse the enzyme again. So to avoid this kind of problem, that lot of industry they use the immobilized enzyme for different industrial applications. Now that so what is called immobilized enzyme? If you look at here, that immobilized enzyme is defined as the localization of enzyme cells or enzyme in a distant support or solid matrix. What I want to say is, suppose this is a solid matrix and this is the enzyme and which immobilized on the surface, or maybe your enzymes has some kind of pore. Inside the pore the enzymes are located. Here it is, this is the enzyme, the pore that is located, or it may be encapsulated inside this inside the membrane. Enzymes are that we immobilize that. So that is why we call it immobilization is defined as a localization of cells. We can have cells or enzymes in a distant support and solid matrix. The support and solid matrix on which the enzymes are immobilized allow the exchange of media containing substrate, effector or inhibitor molecules, and immobilization enhances the stability of the enzyme, because this is stability of the enzymes is a very important factor, as you know that enzymes is like our battery dry cell that we have. If you keep the dry cell for longer period of time, the power will be exhausted. Similarly, the enzymes, if you will keep it idle for longer period of time, the activity will be lost. So, battery also has two type of life. One is called operating life, another is the shelf life. Enzyme also has two life. One is shelf life, another operating life. That if you want to use the enzyme continuously, then after some times the activity of the enzymes will be decreases to a great extent. Even if you keep the enzymes in the refrigerated conditions for longer period of time, you will find the activity lost will be there. So, so stability of the enzyme is a great concern. This can be enhanced with the help of this immobilization techniques. Now that 1969, the first commercial application of the immobilized enzyme technology was realized in Japan using the Aspergillus oryza, the amino acylase for the industrial production of L-amino acid. Consequently, that pilot plant processes were introduced for the production of 6-amino penicillinic acid from penicillin G, and also we know that glucose can be converted to fructose with the help of immobilized isomerase enzymes, glucose isomerase enzymes. So there are tremendous potentiality we have as far as immobilized enzyme is concerned. The advantage of immobilized enzyme, we have it is stable, as I told you, and more efficient in function, and can be reused again and again. I mentioned that, and products are free from the enzyme. control of enzyme function is easy, because I can tell you this is a column, and suppose if we pack those enzymes inside the column, so we can pass the substrate one end and take out the product is on the other end. The enzymes will be immobilized on the solid matrix, that will not go out. So it is free form enzymes. So the control will be very easy, and suitability for the industrial and medicinal use. I can give a typical example that we have, due to some genetic disorder, some human beings we cannot produce some desired enzyme, and so those enzymes might be very essential for the survival of our of the human beings. So you have to supply those enzymes. So this can be supplied in two different ways. Either you take in the form of tablets, or if you immobilize the enzyme on the solid matrix and keep it in the bloodstream, so that blood can take the enzyme can be converted this whatever substrate present in the bloodstream to the desired product. So that the tremendous application we have. Then minimum effluent disposal problem that we have, as I mentioned, it is your product, your effluent will be free from the your enzymes. And let us see the applications. The application, as I told you, that we have a different application: industrial application, biomedical application, food industrial application, textile industry, and detergent industry. Now, in that, if you look at the industrial application, we have the antibiotics. Just now I pointed out 6-aminopenicillinic acid that produce from penicillin G. Then beverage industry, we have I can tell you that that steel proof beer can be produced when we pass the beer through the immobilized protease enzyme, so that whatever big protein molecule is there, that will be degraded into small molecules. Then you have amino acids. Then biomedical applications we have, particularly I want to point out in the diagnostic purpose, for the analytical purpose largely used. Suppose we want to find out a trace amount of any chemicals present in the blood, that can be easily detected with the help of that immobilization, with the help of biosensor. Then food industry, we have jam, jelly, and syrup. Textile industry is covering and biopolishing, and detergent industry we have lipase for the removal of dirt. Now this is the industrial application of different enzymes that we have. One is oxidoreductase, hydrolysate, lyase, and isomerase. So this is the different enzymes like catalase, glucose oxidase, lipo oxidase, peroxidase. So this is used for different purpose. Catalase is used for sterilization of milk. Glucose oxidase, removal of glucose from the food. Then lipo oxidase, that is bleaches the white bread, and peroxidase, paper industry. So that we have different tremendous potentiality we have as far immobilized enzyme is concerned. Now that one important concern that we have with the immobilized enzyme is the solid matrix. This solid matrix or support matrix, where that enzyme that resides or that stick on the surface, the characteristics of the solid matrix plays very important role. Now what should be the property of the solid matrix? It should be inert, because it shouldn't react with the protein molecules. Then it should be strong and stable, because that whenever we immobilize the enzyme on the solid matrix, that your solid matrix is the insoluble mass. Even your enzyme might be soluble. So what is happening, that it will be, when you immobilize it will be insoluble mass. So naturally in a liquid solution, that will settle at the bottom. So what you have to do, you have to do some kind of stirring, and for stirring you have to have some kind of shear forces. So it should be stable and strong. Otherwise, the degradation will take place. It should be cheap and it should be regenerated. Regenerated means we can use it again and again, and surface available for the enzymes, that if the solid matrix has greater surface area, then more enzyme can be immobilized on the solid matrix. Now, if you look at the examples of the solid matrix, there are numerous. As for example, we have it can be divided into three different types. One is natural polymer, another is synthetic polymer, and is the inorganic. So three different type of immobilized solid matrix will be there. Now, natural polymer, we have polysaccharide, cellulose, like cellulose, dextrin, agar, agarose, chitin, and the alginate. Protein, we have collagen and albumin. Carbon. The synthetic polymer, we have polystyrene and other polymer, polyacrylate, polyacrylamide, etc. Now, inorganic material, we have bentonite clay, and silica, and glass, that is largely used by the industry. Now, if you look at the immobilization technique, there are different techniques, and broadly enzymes can be classified in two different types. One is called what you call the insoluble enzymes, and another we have soluble enzymes. Now, in case of insoluble enzymes, that whatever immobilization techniques are used, broadly divided into two types. One is called binding, another is called entrapping. Binding, we have different types. We have cross-linking and carrier binding. Cross-linking means suppose we use some kind of chemicals which has two functional group, two side, so that it can hold one enzyme one side, another enzyme another side, so that it will be cross-linking like this. And carrier binding means in case of solid matrix, the enzymes are that binds with the carrier. It can be of different types. It can be the physical adsorption, ionic binding, metal binding, and covalent binding. Now, as per entrapping is concerned, entrapping means entrap within this system. As for example, I can tell you fiber entrapment. Suppose this is fiber, and inside the fiber your enzymes are entrapped. So this is called fiber entrapment. Suppose you have gel. You have different type of inside the gel, your enzymes are entrapped. This is called gel entrapment. And micro encapsulation, I was talking about a capsule, that in the day-to-day life, if we have some health problem, we use the capsule, and inside the capsule we put the medicine. Similarly, the membrane, inside this we put the enzyme like this. This is called encapsulation. Now, in case of soluble enzymes, two technique we use. One is called ultrafiltration, which is that depends on the pore size of the carrier and the hollow fiber devices. These are the different immobilization techniques that we use. Now, first is the entrapment. I showed you, I told you that how it is. This is just entrap inside this. This is the gel. Inside the gel, the enzymes are entrapped. That is. Then we have membrane entrapment, that hollow fiber inside the fiber, that your inside the fiber that enzymes are entrapped. Then we have micro encapsulation. I told you this. This is the membrane. I told you this. You look at this is the enclave, that is the membrane, and inside the membrane you have the enzyme, that is the encapsulations. I try to explain. And this is the adsorption. This is the most simplest technique, because thus on the solid matrix the enzymes are immobilized on the surface. This is due this type of attraction is mainly due to Van der Waals type of forces, and you know the Van der Waals type of forces is very weak. So little shear force, if you pass liquid and little shear force, what will happen? Take the enzyme away from the solid matrix. So this is very simple technique, but but the problem is that the bonding between the solid matrix and the enzymes is very weak. But most strong bonding that we have in case of this covalent bonding, this covalent bonding appears to be the most strongest bonding, and you see that there is a link, there is a bond between the support material and the enzymes, and this is the electron sharing, and due to sharing of electron, it holds the enzyme very tightly. So it is the very strongest, but for doing so, we shall have to treat the solid matrix with the chemicals, and then and only then chemicals and the enzymes, and then and only then it will be covalently binding. So during this process, there is a loss of activity of the enzyme that take place. That is the major drawback of this process. And this is the examples how covalent binding take place. I have given the instances. So suppose this is CMC, carboxymethyl cellulose, and this is when treated with methyl alcohol and HCl, it forms this hydrazide, and then this hydrazide undergo diazo reaction. It produces acid azide, and this acid azide, this in presence of the protein molecule, we know the protein molecule has the amino group. This amino group will be bind here, and this is how the bond formation take place in case of covalent bindings. Now cross-linking, I was talking about that. Cross-linking is like this, that suppose this is the cross-linking. I can show you. This is the enzyme, and this enzyme is bind with another enzyme. This enzyme bind with another, and this one. This is the kind of cross. So here we have the cross-linking agent, and if you look at the cross-linking agent that we have, that the commonly cross-linking agent is a glutaraldehyde. So in this method, the immobilized enzyme is directly linked with covalent bond between the various groups and polyfunctional reagent. So this has two functional group, in aldehyde group, glutaraldehyde. So due to this aldehyde group, one amino acid hold one side, another amino acid hold another side. This is how the cross-linking take place. Now, when we select the immobilization method for the immobilization of the enzymes, it depends on the characteristics. What kind of characteristics we really looking for. So here I want to stress one very important thing: all immobilization techniques are not suitable for all enzymes. So we shall have to find out what actually we are looking for a particular enzyme. So let me give certain example. Suppose here is the characteristics. Am I right? And what are the different characteristics we have? We have preparation, cost, binding force, enzyme leakage, applicability, running problem, matrix effect, large diffusion barrier, and microbial production. Now question comes, what we are looking for. Whether we are looking for the preparation of the immobilized enzyme, this will be very simple, or we are looking for the binding force between the solid matrix and enzyme will be strong, or we can find out that matrix effect, what should be the matrix effect is there, applicability is wide applicability is there. So cost, whether you can incur lot of expenditure. I can give a typical example. In case of preparation of this biosensor, usually we use the platinum foil. Am I right? Now platinum foil, as you know, platinum is more costly as compared to gold. So but platinum has greater application. Why it has a lot of application? Because though we are using the platinum foil, but the platinum foil we can reuse again and again, because when the activity of them goes down, then we can just we can place it in the oven and burn the organic material again, reuse the foil for the immobilization of the enzyme. So you can 1,000 times more than that you can use the foil for the immobilization purpose. So if you use that, you consider the regeneration of the solid matrix, then you will find that this is the platinum is quite good. So question comes, I want to take the 2-3 instances. Suppose preparation, if you look at that, adsorption is very simple, and covalent is very difficult, and entrapment also difficult, and membrane confinement also simple. Now, if we want the very simple technique, our choice, we have two choices, either we should go for adsorption or membrane confinement. Now, in the cost if we consider this is the adsorption is low cost, covalent binding is high cost, then entrapment is moderate cost, and membrane confinement is the high cost. So, if we want to have low cost, then obviously our choice will be adsorption. So, this is the binding force. The force, if we want to have strong binding force, then we will go for covalent binding. So, depending on your requirement, you have to select that what immobilization techniques you should use. Now, next question that arises, how you express the activity of the enzymes. So, activity of the enzymes can be expressed as that micromoles of substrate converted per minute per gram of immobilized enzyme. This is how the activity is expressed, and activity of immobilized is highly sensitive. It depends on several factors. One is the initial substrate concentration of immobilized enzyme, temperature, pH, reaction time, agitation or flow rate, and the physical dimension of the carrier. So, there are several factors that affects the and characteristics of the immobilized enzyme also depends on other factors like bound enzyme concentration. This is usually expressed as milligram protein per gram of carrier. Then specific activity of the bound protein, it is almost similar to our enzymes. Now, this is very important. So in case of immobilized enzyme, we come across the coupling efficiency. Coupling efficiency means, suppose this is a column, you want to immobilize the enzyme here. So, first you prepare a enzyme solution here, and with the help of pump you take the enzyme here, am I right? You take out and you take it back here. So, this is you recycle again and again until this is saturated. So, what is the coupling yield? The overall activity of the enzyme immobilized. How we can find out? Suppose initially enzyme activity is E0, and when it is saturated, enzyme activity is E1. So, how much activity of the enzyme immobilized is the E0 minus E1. What is the overall activity of the initial enzyme solution is E0. This ratio is give the coupling yield. Now, major problem that we face with this immobilized enzyme is the mass transfer, because this is the solid matrix. Suppose this is the solid matrix, and your enzymes are here and substrate is here. So, substrate has to diffuse to the surface of the enzyme, and then and only then the product formation will take place, and product has to diffuse to this is bulk. Am I right? So, you know that diffusion is a major problem as far immobilized enzyme is concerned. So, what I have pointed out here, you see that mass transfer resistance may introduce the immobilized system which is absent in free solution of the enzyme. In case of solution, enzymes and substrate, they freely interact with each other, but when as soon as you immobilize the enzyme, they are not freely interact with each other. Substrate has to diffuse onto the surface of the solid matrix, then and only then reaction take place, and after the reaction is over, product has to diffuse to the bulk. The mass transfer resistance occur due to the large particle size of the immobilized enzyme and due to inclusion of the enzymes in polymer matrix. Now, the effect of mass transfer resistance, the hypothetical path is like this, that transfer from the bulk liquid to the relatively unmixed liquid layer surrounding by immobilized enzyme, diffusion through the relatively unmixed this liquid layer, diffusion from the surface of the particle to the active site of the enzymes at the inner support. I think next slide we have represented in a pictorial form. This is the substrate, this is the bulk, am I right? Bulk is diffused to the surface, and this is the stagnant zone, it comes like this, and then it diffuse here. So, this is step 1 and 2, external mass transfer diffusion, and step 3 is the interparticular mass transfer diffusion that take place. Here question comes why I try to discuss that how the external mass transfer diffusion problem can be explained. Now here you see that the rate of mass transfer can be expressed by Ns equal to Ks A into Sb into S. So what does it mean? This is Ks A is considered volumetric mass transfer. This is called volumetric mass transfer. Am I right? Mass transfer. And Sb is the concentration of substrate in the bulk, and S is the concentration at the surface of the solid matrix. So this is the dragging force. Sb minus S0 is considered as a dragging force. So rate of mass transfer, and this is the rate of reaction. So this is equal to this. Am I right? Now if you look at that if you do that Ks A Sb minus S equal to Vmax S Km plus S. Am I right? And what I can write Ks A Sb, if I take common 1, I can write S by Sb, and this I can Vmax I can take it here, and this is equal to S by Sb divided by Km by Sb plus S by Sb. I can take 1 by Sb common. So if I assume Xs equal to S by Sb, and and beta is equal to Sb by Km, and this we know Damkohler number. Damkohler number, what is Damkohler number? Damkohler number is equal to maximum velocity of reaction divided by maximum mass transfer. When the mass transfer will be maximum, when S will be 0. If S equal to 0, your dragging force will be maximum. Now if you put this value here, then what will get? 1 by dA, and this is what 1 minus Xs. This will be equal to, this is what Xs, and this is beta, 1 by beta. Am I right? So I can write 1 plus Xs beta, and this beta will come here. So this is we can find out, and we can find in the subsequent that we have derived this equation. This is how we can do that, and dA is known as the Damkohler number, which is the ratio of maximum reaction rate over the maximum mass transfer. Now similarly, now here the interesting feature is that how you can find out whether it is diffusion control or whether it is mass transfer control. Now if the Damkohler number, I have mentioned what is the Damkohler number. Damkohler number is equal to maximum velocity of reaction divided by maximum mass transfer. Am I right? This is the mass transfer. Now if it is greater than 1, if you get at less than 1, less than 1 means what? This will be very less and mass transfer will be very high. If mass transfer is very high, then mass transfer is not limiting. What is the limiting? Is the rate of reaction. So rate of reaction is depends on the control by the substrate concentration. But when your Damkohler number is greater than 1, then your velocity of reaction is very high, or mass transfer is very less. So your rate of reaction, overall rate of reaction, controlled by the mass transfer. This is called mass transfer control. Okay. Now again, there is a parameters called effectiveness factor. That effectiveness factor determines that how it affects the diffusion affects the rate of reaction. This is the actual reaction rate divided by rate of reaction when there is no mass transfer limitation. That means when all substrate is available for the reaction. Now this is like this, and if we do the similar analysis, we can come across this equation. Now the important thing is that if you put x is equal to 1, what will happen? That eta will be 1. Am I right? Then if eta is 1, there is no mass transfer limitation problem. So this is I have shown in the subsequent slide that here you see that x is equal to 1. the concentration the surface is equal to the bulk solution, then which indicate no mass transfer diffusion. But x tends to 0, then mass transfer is very slow as compared to the reaction rate. So then that means that it is diffusion control that we have in the system that we. Now I want to show you one problem that how we can solve. Suppose glucose is converted to fructose by using glucose isomerase enzyme. Find the height of immobilized enzyme column. Following data are given. Diameter of the column is 5 centimeter. Particle size 30 to 40 mS. What do you mean by 30 to 40 mS? That I can tell you that the 30 mS means approximately this is 1 by 30 inch, approximately, not exactly, and 40 mS means that it is approximately 1 by 40 inch. So you have sieving machine, we have sieving plate, and in this pore size is 1 by 30. That 30 mS means bigger size, and 40 mS means smaller size. So in a sieving plate, that if the particle pass through 30, written by 40, we call it 30 by 40. If suppose it pass 40 and written by 50, we call 40 by 50. So this is like this. So here it is given that 40 by 50 means, and then feed rate is 500 milliliter per hour. The glucose concentration at 60 degrees centigrade is 500 grams per liter. Glucose conversion efficiency is 60%. That viscosity is 3.6 centipoise. Feed density is 1.23 grams per liter, and diffusivity is given, and void fraction is given. So question comes how you can find out. So you have to basically find out that height of the column. The height of the column means that what I want to point out here, that suppose this is the column, and you want to pass the substrate here, and you have to find out what should be the height of the column to get the 60% conversion of the substrate. So here we have Z we consider as the height, and there the Satterfield equation that we have, the epsilon in the RE is the Reynolds number, this is the Smith number, Y1 is the mole fraction of the substrate of the feed, and Y2 is the mole fraction of the substrate in the outgoing stream. So this if we analyze, I have solved this equation here, that we can from this data we can easily find out what is the velocity of the fluid, that the volumetric flow rate is given, cross sectional area, and as you know volumetric flow rate means volume per unit time, am I right? And what is cross sectional area? That is cross sectional area is the centimeter square, and volume is usually centimeter cubed or milliliter, what do you have. So if you cut, it will be in centimeter. Centimeter per unit time is the velocity. So velocity you can easily calculate here. Then we can find out the Reynolds number. Reynolds number is the kind of flow characteristics of the fluid. This the equation is given. Smith number, it deals with the diffusivity of the particles through this for this immobilization system. This is the equation that we have. All this value you can find out, and AB is the surface area of the particle divided by volume of the particle. This we consider the spherical particle. Spherical particle area is 4 pi r square, and volume is 4 by 3 pi r cubed. So we can solve, and we can find out this is the ratio that we have. And then if we put all these values in this equation, we come across this height. That is height come 2.2889 centimeter. So this is how we can find out the height of the column to get the desired 60% conversion of glucose to fructose. So in this particular lecture, we try to understand that what is the advantage of using immobilized enzyme system, and what are the different techniques is used, how we can characterize the immobilized enzyme, and we also come across that how you select the immobilization techniques. Different immobilization techniques are there, and then I discussed the diffusion problem. I discuss the external diffusion problem, not interparticular diffusion problem, and how you can find out how the effectiveness factor and time Coulomb number can be calculated, how you can find out whether the reaction is mass transfer limitation or the reaction controlling, that we can find out. Thank you very much.